Okay, so here the charge of the density, if we look at number 2, is given by this formula. And right away I see the x squared plus y squared, so I know I'm probably going to have to change to polar coordinates. So the total charge, remember, is a double integral over the object, or the plate. And in number 2, we'll read the problem. It's distributed over the disk, x squared plus y squared equal 4, and we want the total charge on that disk. So if we go this way, we have y equals the square root of 4 minus x squared. Here we have negative 4 minus x squared. Okay, and then we're going from negative 2 to 2 since the radius of that circle is 2. So we're going to go from negative square root of 4 minus x squared, square root of 4 minus x squared, negative 2 to 2 of the charge, the density charge. Okay, let's change that to polar though. I think it'll be a lot easier. In polar coordinates, this is r equal 2. We know r is between 2 and 0, and we're going around the whole circle, so theta is between 0 and 2 pi. So we're going to go 0 to 2, r cosine theta plus r sine theta plus r squared. This right here is r squared dr. And then for theta, we're going to go from 0 to 2 pi. Now, we can use Maple to integrate this. I'm going to integrate it with respect to x and y. So let's open Maple. Let's do x and y first. We have the integral of x plus y plus x squared plus y squared, y equal negative square root of 4 minus x squared to square root 4 minus x squared. Okay, and then we're going to integrate that where x is negative 2 to 2. So we get 8 pi. Now let's do it using polar coordinates. I have r times cosine theta plus r times sine theta plus r squared times r. Okay, I forgot about that. You have to always have r dr d theta. So we're going to go from 0 to 2 first. Okay, let's see. Got equals. Okay, now I want to integrate that. Theta goes from 0 to 2 pi. You need a capital P in the pi. Should get the same answer. Yes, we do. So Maple, we can use that to integrate for us. And let's go back and fix this. When you do polar coordinates, and I always forget this too, you need an RDR here. So make sure you put that extra R in there. All right, let's look. I'm just going to set that one up and use Maple to work it out. Let's look at number 8. And number 8 says I want the center of mass with D bounded by y equals square root of x, y equals 0, x equal 1, and the density function is x. So I have this picture. That's what the plate looks like. The mass is the integral over that plate of the density times dA. So if I go this way, I'm going to go from the square root of x to 0 dy, and then cutting up the x-axis, I'm going to go from 0 to 1 dx. So working that out, that's not too hard. It's going to be x squared over 2, 0 square root of x. No, I'm integrating with respect to y, sorry. If I integrate with respect to y first, then that's going to be xy. And I'm plugging these into y, so that's x to the 3/2. And I don't want an equal sign here because that's not equal. I'm just doing the first integration. Okay, now I want to integrate x to the 3/2 with respect to x. So I get x to the 5/2 times 2/5, 0 to 1, and I get 2/5. Now the moment my is the integral of x times the density function times dA. Okay, so we're just going to go again from 0 to 1. That limits are the same of x squared dy dx. So that's going to be x squared y. 0 squared of x is x to the 5/2. Then I'm going to integrate that with respect to x is x to the 7/2 times 2/7, which is 2/7. And mx is y x dA. With respect to y, okay, I don't equal that. That's going to be xy squared over 2, 0 square root of x. That's going to be 1/6. So the center of mass is going to be x bar, which is moment with respect to the y-axis, which we found was 2/7, and the mass was 2/5. So this is 5/7, and y bar is mx over m, which is 1/6 over 2/5, which is 5/12. So the center of mass is 5/7, 5/12. Okay, that should help you with your problems.